Hi, let's now look at the integral transforms. After discussing Fourier series, now we are in a position to discuss about Fourier transform. We know the Fourier series representation is the representation of a periodic function, in a fixed interval as the superposition of sinusoidal functions, sines and cosines. So the function has to be periodic. So one of the conditions for representing a function f of x as a Fourier series expansion, it has to be periodic. Okay, but we may have functions which are defined over an infinite interval, rather a function defined in a finite interval, okay, or a function defined in a finite interval and with a definite periodicity. We might be having functions which are defined in infinite interval, okay, infinite interval, okay, and there is no periodicity, no particular periodicity, okay, no particular periodicity. Okay, so the function is not at all periodic. So in that case, we represent such functions as Fourier transform. Okay, in that case, we are representing the functions by Fourier transform, and this in the representation is called integral transforms. Okay, Fourier integral transforms. So what is Fourier transform or Fourier integral transform? Fourier transform provides a representation of functions defined over an infinite interval. Okay, not a finite interval as in the case of Fourier series, and having no particular periodicity. Okay, no particular periodicity. So there is no condition such as the function has to be periodic. So no particular periodicity in terms of a superposition of sinusoidal functions. So this is Fourier transform. Okay. So Fourier transform is this. We are representing a function as a superposition of sinusoidal functions where the function is not defined in a finite interval. Actually, it is infinite and there is no definite periodicity. Okay. The Fourier transforms are often used to represent time-varying functions. Okay. So instead of f of x, we will be using f of t. In Fourier series, we used f of x, but here we will be using f of t. Okay. So we are finding the Fourier transform of f of t. Okay. Instead of Fourier series of f of x, we find this. The only requirement for f of t is integral minus infinity to plus infinity f of t dt is finite. So this has to be finite. Okay. Now let's look at the Fourier integral theorem. We first of all develop Fourier integral. Okay. First of all, we develop Fourier integral. The Fourier integral is defined or is obtained from Fourier series that we learned in the previous classes. We know that Fourier series of a function f of x in the range minus L to plus L is given by f of x equal to a0 by 2 plus sigma n equal to 1 to infinity an cos n pi x by L sigma n equal to 1 to infinity bn sin n pi x by L. So, Fourier series of a function f of x in the range minus L to plus L is given by this, where a0, a1, an, bn, these are coefficients that can be obtained like this. The a0 is this 1 by L minus L2 minus L2 plus L f of x dx. Okay, 1 by L integral minus L2 plus L f of x dx. And as we saw earlier, instead of f of x, we will be using f of t. Okay, we are actually using f of t. So, we are writing it as a0 as equal to 1 by L integral minus L2 plus L f of t dt. Since we are using t, we have f of t dt. So, this is a0 and an is this. So, this is an 1 by L f of t cos n pi t by L dt, and bn is 1 by L integral minus L to f of t sin n pi by n pi t by L dt. Okay, so we have a0 with us, an with us, bn with us, that we substitute here. For a0, an, bn we substitute. So we will be getting f of x. Okay, we started with f of x, so we can see f of x as equal to 1 by 12. We substitute for a0 here, and here we substitute for an. Okay, and here we substitute for bn. Right. So in the Fourier series that we saw here, we substitute for a0, an, and bn. Okay, and we have f of x now as equal to this. This is a0. A0 by 2 is there, so 2 comes here. Then we have this an, this is an, and this is our bn. Okay. So once we have that, we can write, since here we have cos n pi t by L, cos n pi x by L, and sin n pi t by L, sin n pi x by L, and everything other is same, 1 by L. We can take this sigma n equal to 1 to infinity, 1 by L as common factor. So that is written here. This is L, and f of t is missing here. Okay, so this will be our f of x. So f of x is now given by this 1 by 12 integral minus L2 plus L f of t dt, and I am taking this sigma n equal to 1 to infinity 1 by L integral minus L2 plus L f of t as common factor is there. Then we have this, and as we look at this, we can see it is of the form cos a minus b. Okay, this is of the form cos a minus b. So we substitute that, or we represent this in the form cos a minus b. So we have cos n pi by L t minus x dt, and here it is L, here it is also L. Okay, this is minus L2 plus L. Okay, here also we have minus L2 plus L. Okay, so once we have that, we can represent, see, when we look at here we have L f of t integral. Here also we have this. So I am taking 1 by 2L integral minus L2 plus L f of t as common factor. Okay, 1 by 2L minus L2 plus L f of t is taken as common factor from this. Okay. So we have that is that we take as the common factor. So we have 1 plus 1 plus 2. This 2 and 2 will get cancelled, so we will be getting 1 by L here in this equation. Sigma n equal to 1 to infinity cos n pi by L t minus x dt. And since cosine function is an even function, that is cos minus theta is cos theta. So here suppose I take minus n for negative values for n or positive values for n, both will be giving us the same result because it is an even function. So it is immaterial whether the value of n is positive or negative. Okay, so I am writing this 1 plus 2 sigma n equal to this factor as sigma n equal to minus infinity to plus infinity cos n pi by L. So the value of n can be positive or negative, and it will give the same, it will yield the same value. So you have this 2 that you will get. Then this 1, that is for n equal to 0. When you vary n from minus infinity to plus infinity, in the middle you have n equal to 0. So when you put n equal to 0, this will be 1. So that value 1 you will get. Okay, so instead of this in the expression, I can write like this. Okay, so I am writing for this 1 plus 2 sigma n equal to 1 to infinity cos n pi by L t minus x. I am writing sigma n equal to minus infinity cos n pi by L t minus x. Okay, so that I am doing here. So I have f of x as equal to 1 by 12 this, and here I am writing this. Okay, so the next step, what I am doing is I introduce, here I have 1 by 2L. So I make it 1 by 2 pi, and pi by L is introduced here. So this pi will get cancelled, and you will have 1 by 2L. Okay, so here I am introducing pi, and that pi by L is taken along with this. Okay, now suppose that L increases indefinitely. Okay, L is increases indefinitely, that means L becomes infinity. So what you have is minus infinity to plus infinity. Instead of minus L to plus L, okay, minus L to plus L, you have minus infinity to plus infinity. Okay, and here this is taken as u. Okay, n pi by L is taken as u, and here the value of n changes in steps of 1. It changes in steps of 1, so that delta n is 1. For the change in value of 1, you have du as equal to pi by L. So n pi by L is u. If you take n as 1 or delta n as 1, you could have taken delta n pi by L. Okay, delta n pi by L. For delta n is equal to 1, delta n is definitely 1 because the value of n changes in steps of 1. So you have pi by L as equal to d by. So this is actually this is actually du, and this is u. Okay, this is du. Okay, and n changing from minus infinity to plus infinity. N is now Lu by pi. Okay, n is now Lu by pi. So what we can write is this: sigma, limit L tends to infinity, pi by L is du, And this factor sigma n equal to minus infinity to plus infinity, that can be written as we are actually converting this into what? This into kind of integral. Okay, this is taken as du. Pi by L is taken as du, and this is u. So we have cos u t minus x du. Okay, where u changes as n changes from minus infinity to plus infinity. As n changes from minus infinity to plus infinity, u will be changing from minus infinity to plus infinity. Okay, here as n changes from minus infinity to plus infinity, u also will be changing from minus infinity to plus infinity. So what essentially you are getting is this. This term now becomes integral minus infinity to plus infinity cos u t minus x du. And since cos u t minus x, that is a even function. Okay, this is even. What we can do is this integral minus infinity to plus infinity can be written as 2 times integral 0 to infinity cos u t minus x du. Okay, so this term, okay, when limit L tends to infinity, this term will become like this. So f of x here, originally f of x is here, this integral is there, minus infinity. This L now, L is changing to, tending to infinity. So this will be minus infinity to plus infinity. Okay, and this term becomes 2 times integral 0 to infinity, like that. Integral 0 to infinity, what? The cos u t minus x du. So that we substitute here. So as we substitute, you get f of x as equal to 1 by 2 pi integral minus infinity to plus infinity f of t 2. This we are substituting. Okay, you know why this becomes minus infinity to plus infinity? Because L is changing to infinity. So you get f of x as equal to 1 by pi integral 0 to infinity integral minus infinity to plus infinity f of t cos u t minus x du dt. Okay, dt du. So this is a double integral, and this is actually the Fourier integral. Okay, this is said to be this double integral. Okay, this double integral means here we had changed this into this 2 times this. Suppose I keep like this. Okay, if this is kept like this, integral minus infinity to plus infinity cos u t minus x du, and then if you substitute, you will be getting this f of x as equal to 1 by 2 pi integral minus infinity to plus infinity f of t integral minus infinity to plus infinity cos u t minus x du dt. This double integral is known as Fourier integral. Okay, which can be also written, since this is an even function, I can write this as integral 0 to infinity this. Okay.